New identities. So everybody look at your papers. You don't have to write this down because you have this on your paper that you picked up on over by the door. So we already know all of these ones. We know the reciprocals, and then we know that tangent can be sine over cosine, and then cotangent can be cosine over sine. Then remember that sine squared u plus cosine squared u equals 1. That's what I call the original identity. And then we can take and manipulate that, like we can subtract cosine squared over and get that. So this would be a true statement. We can then take this and subtract sine squared, so this would be a true statement. Now, once again, keep in mind the reason we're doing identities, to make something smaller. No fractions and one term, if possible. So what would be better? And if I'm in your way, just move to like you guys, because I'm going to be covering. If you need to move, move. So, because I'm not going to try to open up. Does that make sense? We've got to go quick. So what would be better, to have two terms or one? One. What would be better, to have two terms or one? One. And do you see what I'm saying? You would change that to be this. That's the point. Like, why do we have all these? Because this is better than this. No fraction is better than a fraction. Okay. Next thing, the next trig identity is 1 plus tangent squared theta is equal to secant squared theta. And then we can take and manipulate the original to get these true as well. So once again, this would be better. This would be better, and that would be better. More simplified. So this is also a true one. This should be squared. So 1 plus cotangent squared is cosecant squared. So then we could take this and manipulate it. And we would get these as well. So this is the original. One thing I do want to point out, I'm going to go back to this one. Careful, because order matters here. Like this is positive 1 and negative cosine squared. So if we were given cosine squared u minus 1, you got to look at it and make it better, correct it. Does that make sense? You've got to be careful. Those are not the same thing, are they? So you've got to look at it and change it. Okay. All right, these are new to us. So sine of pi halves minus u will be equivalent to cosine of u. So what would be considered prettier is this one, because that's kind of ugly. Now this will always be true. So watch it actually be true. Let's take an easy example. Let's say that we're looking at u is pi halves, okay? So this would be sine of pi halves. Sine of pi halves minus pi halves, which is sine of 0. The sign at 0 should be equal to, now we're plugging in pi halves, should be equal to the cosine at pi halves. Do you see what I'm saying? Let's check to see if that really works. The sign at 0 is 0, correct? The cosine at pi halves is 0. Do you see how they're equal? So once again, this is prettier than this. So look, sine and cosine go together. Cosine and sine go together. Tangent and cotangent go together. So then if sine and cosine go together, their reciprocals will go together. So that's kind of a way that helps me remember these and memorize these. These are on your paper. If you need to take notes on your paper, you can. Okay, remember these are even and odd identities. So even functions, odd functions. We've talked about this a few times this year. So sine is odd. So if sine is odd, then when we plug in a negative here, then it will simplify to be -1 times the original. Also, tangent is odd. So if you plug in -1, it will be the same thing as -1 times tangent of u. Now, what is considered more simplified is to bring the negative out. So this side would be better than this side. Okay, next thing is cosine is considered an even function. So if you plug in a negative, it will simplify to just be the original function cosine of u. So this would be prettier than this. A negative, like anything inside, we would rather have it on the outside. Okay. All right, so here we just get right to the examples now. Use the values. This is a review problem. This is not an identities problem, a review problem. This is use the values. Secant of u is equal to -3/2, and the fact that tangent is greater than 0 to find the sixth trig function. So first of all, this is not on the unit circle, is it? That's not a simplification of the unit circle. So you'd say, okay, well this must be a right triangle trig then. So I put it at right triangle. I put a theta. Secant is the reciprocal of cosine. Cosine is Adjacent over hypotenuse, so this must be hypotenuse and adjacent. So my hypotenuse is 3, my adjacent side is 2. Remember, hypotenuses are never negative, so the negative must have been with the 2, even though it kind of looks deceiving because it's on top. Now here's what else it gives us. It says tangent is greater than 0. So what you should say is that's sine over cosine. Or, in other words, y over x should be larger than 0. Well, we know x, y, we know x is negative. So to make this true, would y be positive or negative? It needs to be greater than 0, so it doesn't need to be positive. In order for this to be positive, y must be negative as well. So we would put a negative, and then we would go through and find this side. So we would do 3 squared minus negative 2 squared equals question mark squared. 9 minus 4 equals question mark squared. So the square root of 5 equals question mark. So it's negative root 5. And now we can do sine, cosine, tangent. Secant, cosecant, cotangent. I'm not going to list them all out. Everybody good? That was review. Okay, here we go. Let's start using our ideas of trig identities to get this to one term, if possible, and no fractions. So simplify the trig expression. Also remember our favorites for the most part are to get sine, cosine, and tangent as long as it's not a fraction. So looking at this, we have sine of x times cosine squared of x minus sine of x. Do you see how there's no fractions here? And then right here, sine of x. Those are all pretty good. Like, that's pretty simplified. So really, the only thing we could do is possibly say, is there something in common in each term that we could factor out? A sine. Does everybody see? So let's rewrite this and just see what happens. Maybe that won't even help us. It might though. So let's try it. But then if you look at it and it doesn't help you, you can just put it back together. So I'm factoring out sine of x. So divide by sine. Divide by sine. So then let's see what's left in our parentheses. In the first term is cosine squared x. And then we have minus 1. Now, the reason I'm looking at this saying, oh, you know what, actually, that is a little bit helpful is because that looks really close to a trig identity we know. Here's the trig identity we know. Sine squared x plus cosine squared x equals 1. So isn't this a manipulation of that in a sense? So let's do this the correct way, though. We need it to be in this order. Cosine minus 1. Does everybody see? So we need to bring, we don't want cosine to be negative, do we? So I'm going to subtract sine squared over. Is everybody okay with that? So then I would have cosine squared x equals, and then I have negative sine squared x plus 1, because I brought that over here. So then wouldn't I subtract 1? Cosine squared x minus 1 equals sine squared x. Oh, no, equals negative sine squared x, right? If you look at it. So that is negative sine squared x. Are we all seeing it? So we have this. Sine of x times by negative sine squared x, which is what? Negative sine cubed of x, which is one term and no fraction. So that's better than 2 terms. Everybody is doing okay with that one? Okay. Next one. This is number 30 out of the book in the same section that your homework's in case you want to write that down to refer back to. So it's to simplify the trig expression. Now understand there are many ways to go about this, but once again, you all should get to the same answer. It just depends on how quick you want to get there. So the first thing I would look at is to say, well, I see there's 2 terms here. Let's see if we can rewrite that instead as 1 term. If that's true, let's do that. If not, we'll have to tackle this differently. What is that equivalent to? Cosine squared. So we have secant x times cosine squared x. And you should say to yourself, there's many ways to go about this next piece here. However, yeah, you're already seeing it. However, this is how I think most of you would do it, which is great. Some of you can just see the answer. Oh, what would this be? So you're saying that's 1 over cosine squared of x times cosine squared of x, which is, like you are saying, 1. Now, here's the thing, guys. The reason we do this is because when you get to calculus, you're going to be asked to do like integration, which you don't know what that is. Well, if I asked you to integrate, I'm just showing you the reason we're doing this. If I asked you to integrate, there is a nasty problem. It's going to take integration by parts, and it's going to be a huge, long problem. And you could do it and get it right, absolutely. However, if you recognize that this is equivalent to 1, you are now just integrating 1 dx, which is literally the answer would be x. So you don't get what I'm saying, but do you see how that was such a one-step process? This would take a page worth of work, and you get there, it's just going to be a nightmare. So that's the point of this, is seeing how we can write these better. Okay, next one. 1 over tangent squared x plus 1. First of all, I see a fraction, least favorable. Second of all, 2 terms. Can I write this as something different? Tangent squared x plus 1. What is that? So this is 1 over secant squared x. Now what should we do next? What should we do next? Oh. Fractions, least favorable. Go. Cosine squared x. That is way better than having this with all this split apart. No fractions and 1 term. Okay. Tangent squared over secant squared theta. So let's simplify this. Any suggestions of where to start? There's not a wrong answer. We can start wherever you want. Yes. Ruben. Sorry, say that one more time. Oh, you're saying it's secant squared minus 1? Okay, so he's seeing it a way I haven't even thought about before. That is one way of doing it. So you're saying that this is the same thing as secant squared theta minus 1 over secant theta. Okay. Secant squared theta. Okay, that's one way of thinking through it. That is not incorrect. Where would you go next to that, Ruben? So what you should do next, guys, is split it up. So we can split up the numerator. We can't split up a denominator. So secant squared theta over secant squared theta, everybody. Minus 1 over secant squared theta. Do you see why I did that? So then this would become a, so we have 1 minus cosine squared theta. Does everybody see? Which is sine squared theta. I will see Ruben completely thought of it. I would have never done it that way, which is not that he was wrong, completely correct. Do you see how he got the same answer? Let me show you how I would have done it. Not that my way is any better, because it's not. I would have said, okay, secant squared is cosine squared. 1 over secant is cosine. So then this is tangent squared theta times cosine squared theta, right, everybody? Isn't tangent sine squared theta over cosine squared theta? So we have sine squared over cosine squared times by cosine squared theta. So those cancel out. So we get sine squared theta. But once again, it does not matter how quick you get there as long as you get there. Does that make sense? But do you see how one way might be quicker than the other? Yeah. Like I said, it doesn't matter. That was good thinking, Ruben. I love it. Here we go. Cotangent of pi halves minus x times cosine of x. So first of all, that is really ugly. Let's fix this. What is this equivalent to? I'll tell you. Tangent of x. That was a trig identity we just went over. So we have tangent of x is that times cosine of x. Where should we go next? Yeah, tangent sine over cosine. Anytime you see a tangent and a cosine, or a tangent and a sine, you should start writing them as sine and cosine. So tangent sine of x over cosine of x. Then we have times cosine of x. So then what happens? We would get sine of x, since these will divide out. Sine of x is much prettier than all that stuff. Everybody good? Feeling pretty easy? Okay. So this is cosine of t times 1 plus tangent squared of t. T's and plus signs start to get a little ugly, so I'm going to throw some parentheses in there. Okay, once again, the first thing I notice is that there's 2 terms here. If I can, write this as one term, I will. If not, I would distribute in cosine of t and see what happens then. We could do that in the beginning, but I'm just going to rewrite 1 plus tangent squared as secant squared. So you have cosine of t times by secant squared of t. Then you should be saying, what would you say? Yeah. Yeah, what are you saying? This is 1, okay, so you're saying that this right here, he just said that's 1 over cosine squared. Is that true? Mm-hmm. So now what would we get? So we would get 1 over, let's just because some people need to see the work. So you're right, it's going to become secant. So this would be 1 over cosine, wouldn't it? So then that is equal to secant theta, which is no fractions, 1 term, much better. Good job, awesome, guys. You're getting better and better at these. Okay, here we go. So let's start to get into some more advanced ones. So this is cosecant phi tangent phi plus secant of phi. So we can go through and look at each piece and see where we're going with this. Here's the thing. We always want to have just one fraction or one piece instead of 2 pieces. So I'm looking at this. We can look at it and see what we can do with it. Can we simplify that? So cosecant is 1 over sine of phi, and then tangent is sine of phi over cosine of phi. This is just this pink piece, so can't those divide out? So we have 1 over cosine of phi, then over here I have plus secant of phi. Now how I did this in first hour differed to second hour, and now I'm in third hour. I'm curious as to both were correct. Does anyone see where they would want to go next? Yeah. 1 over cosine is secant. Do you see why he's doing that? Okay, true. So this is secant phi plus secant phi, which is 2 secant phi's, which is 1 term. This had 2 up here, and it looks pretty good to me. Good stuff. We're doing good. Okay. All right, it says factor the expression. So this is asking us to factor this. What I want you to notice is this one looks quadratic. It's quadratic in form. We're going to use a technique that we use in calculus all the time, right here, right now. It's called a U substitution. So you're going to be able to replace something with a U, and then you're able to do all the hard math using the U, and then just later go and insert that substitution you made back in. So if you look at this, it looks almost like a quadratic. It would be a quadratic if we said let U be equal to secant theta. That way we can write it prettier. So that would make this U squared minus 1. We do this in calculus because now the calculus on this is really easy. Really easy. So our factoring is really easy here. We do what multiplies to be negative 1 and adds up to be 0. 1 times negative 1. We can quick factor. So this factors to be U minus 1, U plus 1. You'd say, there's my answer. Now I have to just go and put in what U really is. So U was really secant theta minus 1, and then we would have secant theta plus 1. We just factored it using a U substitution to make it easier on us. Then you can check your answer, because if you multiply out that bottom thing here, it should end up back at the beginning, and it would. Everybody good? Hey, you guys, let's look at this one. This is factor. What's our U substitution here? Tangent of theta. So then that would be 4U squared plus U minus 3. Then we'd say we can factor that. What multiplies to be A times C, what multiplies to be negative 12 and adds up to be 1. 4 times 3, correct? Negative 3, positive 4. Careful though, do not quick factor. Look, our leading coefficient's not a 1, it's a 4. So we have to do our technique of drop and break. We drop down 4U squared. We drop down negative 3. We break down the middle term as these two factors but with U's. So plus 4U minus 3U. Then we factor by grouping. We would pull out a 4U, so then left would be U plus 1. We'd pull out a negative 3. Left is U plus 1. I'm factoring like a maniac because I'm sure that this is boring if I went any slower. We all know how to factor. Our safe haven's the same, so we've done this right. U plus 1 and 4U minus 3. We factor out that safe haven and end up here, And then you would say u is really tangent. So then we would have tangent of theta plus 1 for tangent theta minus 3. We've just factored it. Good stuff. Okay, now here's where we run into a problem. It says factor the expression. You say it looks quadratic, but I just did 2 u substitutions where it was really straightforward. Because both pieces were tangent. Both pieces were, well, that was just a secant. So looking at this one, if we try to do a u substitution with cotangent of x, right now that's still going to be cosecant. That's not helpful. If we did u is equal to cosecant x, that would be u squared minus cotangent. It's not helpful. So we thought I'd take this and manipulate it using something that's equivalent to get it either all cosecants or all cotangents, so we can make a u substitution, and it will take care of everything. So either of these, can cotangent be written as cosecant? Can cosecant be written as cotangent? This would be a trig identities thing. So look at your trig identities. Cosecant squared theta is what? Oh, 1 plus cotangent. Wouldn't that be nice? So let's rewrite this as its equivalent. You said it's 1 plus cotangent squared. We just rewrote that in its equivalent form. So then we have minus cotangent x minus 3. So now look, all cotangents. Let's put it in standard form real quick. So we have cotangent squared x minus cotangent of x, and then 1 minus 3. Minus 2. And now we're able to say, okay, so u is equal to cotangent of x after all. So u squared minus u minus 2. We'll factor that. What multiplies to be negative 2 adds up to be negative 1. 1 times 2, negative 2. A quick factor. So it factors to be u plus 1, u minus 2. So then we would have cotangent of x plus 1, cotangent of x minus 2. Good stuff. So if they're not the same, you will be able to use trig identities to make them the same trig function. All right, back to simplifying the expression. So using trig identities. So we have sine of t plus cotangent of t times cosine of t. Let's throw in some parentheses. This is where they start to get, like I said, a little bit more advanced here. Okay, sine of t looks pretty good to me. It's one of the originals. It's not a fraction. I'm going to just wait right now on that one. So let's move over here. What does that simplify to be? Sine of t plus, what is cotangent? Cosine over sine. So let's say, okay, so we have cosine of t over sine of t, and then we have times cosine of t. Now careful, because the cosines do not divide out here. So what we're looking at is actually this, sine of t plus cosine squared t over sine of t. Now, above all, you want it to be one term. One term. We have 2 terms here. You always will, if you end up kind of stuck and you can't simplify anymore, you will put them together. You want one term. So, wouldn't I need a least common denominator? So this is sine of t over 1. We want to put this together. So now we'd multiply this by sine of t, and then we multiply this to sine of t. So now what we have is sine squared t over sine of t plus cosine squared of t over sine of t. Now careful, because guess what a lot of you might do, because you did this on the test, it was at the beginning of the year. When we were doing this, then the next thing you did was redivide these out and end up right back here. Do you see what I'm saying? So remember, what was the point of getting a common denominator? To now add the numerator. So let's combine our numerator. So on top we have this, sine squared t plus cosine squared t. And on bottom, now all over the common denominator, sine of t. Don't be that person that divides those out. Don't be that person. You don't do it across an addition sign. What can we do? Oh, you're saying that's an identity of 1. So we have 1 over sine of t. That is true. Good. And then our last step would be to get rid of the fraction cosecant t. Who would have known that that big nasty thing up there would have simplified to be cosecant t? That's equal equal to cosecant c. Okay. Doing good? Another one. So we have sine over 1 plus cosine of theta plus cosine of theta over sine of theta. Okay, first of all, I want to point something out. There's two terms right here, but we can't change that to be one term because it's not squared. Nothing, so there's nothing we can do to fix this. If I bring sine up, that's not going to fix anything, correct? So what are we going to want to do? We must be having to get a common denominator because we can always put two pieces into one piece with a common denominator. So let's multiply by sine of theta. Sine of theta. This one we're going to multiply by parentheses 1 plus cosine of theta. 1 plus cosine of theta. Now the next step when getting a common denominator is to multiply out the numerators. That's your next step, if you'll remember. So right here we have sine squared theta. Now you do not need to multiply out the denominator, if you'll remember back to adding fractions. So let's leave the denominator factored. You do want to multiply out the numerator, but the denominator I'm going to leave factored. So multiply out the numerator, you got to do that. So right here we get plus cosine theta plus cosine squared theta all over sine theta 1 plus cosine of theta. Now look at the problem. Don't start dividing things back out and get back right to the beginning. Look at it and say, what was the point? The reason we got a common denominator is to then next combine the numerators. So let's put our numerator together. So we have sine squared theta plus cosine of theta plus cosine squared theta. And isn't that all over the common denominator? Well, that's nice, because what do we see happening? Oh, you're saying that plus that is 1? And addition can be reordered in any order, so you're correct. That becomes a 1. So we have, now that doesn't just make it, it makes it plus 1, right? So we would have cosine of theta plus 1 on top. Do you guys all see why? That plus that is 1. So then we have cosine plus 1 over sine of theta times 1 plus cosine of theta. Would it be appropriate to divide out that and that? Yeah, we can divide across an addition sign if it's the whole term, if it's the whole thing. So those whole things divide out, those whole factors divide out. So then we would have 1 over sine of theta, which is equivalent to cosecant theta. How pretty! That other one was really not very pretty. That's not bad. So all that simplified to be cosecant theta. Okay, next one, simplify the expression. We can't split apart a denominator. So there's literally nowhere to go with this. Do you guys see what I'm saying? We cannot split apart a denominator. You can't call this 1 over 1 plus 1 over sine of x. If it was flopped, you can split up a numerator, not a denominator. So there's literally nothing we can do. Now here is the thing though. Fractions are the worst, and having a trig in the fraction, having something trig in the fraction in the denominator is the worst. It's almost as bad as having a radical in the denominator. So we need to get rid of this and make this not have a trig function in there. So the only way to get rid of this, because there's two terms, is to multiply by the conjugate. Now do you remember when we had two terms with a radical? That's how we got rid of the radical. If we had 3 plus root 2, we multiplied by 3 minus root 2. We're going to treat this the same way. We're going to say, let's multiply by its conjugate. 1 minus sine of x. So then on top, we would get 1 times all that stuff. So that's 1 minus sine of x on top. Then on bottom, we would distribute. We would have 1 minus sine squared x. What is sine squared x? I mean, not sine squared x. What is that denominator? Cosine squared x, which is now making it better, because now it's just one term I meant to say. So we have 1 minus sine of x over cosine squared x. Now here's the thing. What's hard is it's like, well, where do we go from here? There's so many ways to go about it. So You said split up the numerator? I like that idea. I don't see anything better happening here. So let's split up our numerator. So we have 1 over cosine squared x minus sine of x over cosine squared x. Well, now at least in that first piece, we can make it secant squared. Oh, where did my little scroll down thing go? Well, can't scroll down. So we have this is secant squared x minus, anyone? Tangent? Yeah, you're right, tangent. Oh, secant tangent. So how is he seeing that? So everybody look what he's doing. He's going, this is sine of x, technically cosine of x, cosine of x. Do you guys see what he's doing? So he's seeing this is a tangent. And this is a secant, 1 over. Does that make sense, everybody? Right here is what we're really looking at. So he's saying this is secant squared x, and then minus tangent of x from that, times secant of x. Now here's the thing, it's like, do we keep going? Do we stop? Like, when you start undoing and getting back to the original, you're going too far. So the next thing I would just check, I just checked one last thing here. I've gotten rid of the fractions at least. Does everybody see? But I do still have 2 terms, but that might happen sometimes. So the next thing I would check is, well, I see that in both terms there's a secant. If I factor that out, is it going to make me able to simplify it more? If not, there's no need. Let's check. If I pull out secant of x, divide by secant x, divide by secant x, left would be secant x minus tangent of x. Is that a trig identity? If so, we would want to do this. If not, there's no point. Is it a trig identity? No. It's squared. You look at it, it has to be squared. So there would be no point. So if I kept trying to simplify this, I'm going to start undoing and going backwards and end up back up here. So I'm just going to stop right here, because once I kept going, there was nothing better to do. Does that make sense? Okay. Okay, this is my last example. Oh, almost. We got to go quick. It says, use the substitution given that x is equal to 2 tangent of theta, where theta is between 0 and pi halves. So 0 and pi halves just means we're in quadrant 1. So it says to write this as a trig function of theta. So it says take this and write it as a trig function of theta. So look, we'll replace that with x. So we have 4 plus, instead of x, we actually have 2 tangent of theta squared. You see how that's x? So we have the square root. Let's simplify this. We have 4 plus 4 tangent squared theta, because I got to square both of those. Now, what can I do? Can I do square root 4 right here? Nope. Oh. Shouldn't I factor out a 4, guys? There's a 4 in each term. So I'm going to factor out a 4. Not factor out, but factor out here. Divide by 4, divide by 4. So then left is 1 plus tangent squared theta. Well, 2 terms. It's better to have 1 term. Can we write that as 1 term? We have the square root of 4 times secant squared theta. Well, because that's a multiplication sign, can't I square root that, square root that? Yes, because it's a multiplication sign. Square root of 4 is 2. Square root of secant squared is secant. Nice. So we're almost done here. Write as a single logarithm and simplify. So we have to know our logarithm rules. When you add, you multiply. So this is ln of cosecant theta times tangent theta. Then you would say, well, that's ln of cosecant is 1 over sine. Tangent is sine of theta over cosine of theta. So we're looking at the ln of 1 over cosine theta, aren't we? So we're looking at ln of secant theta, and that's as pretty as it gets. Just using your logarithm properties. All right, there are the problems. That was perfect timing. We got through the whole lesson with 3 minutes to spare. there's the lesson. I will print out a paper next time with all the assignments on it, but right now you don't have that. So you need this to know what to do your homework of.